Hello, my friends, and welcome to a prospectus on linear algebra. This is more of an experiment to see whether this setup will actually work for communicating mathematics, but I will be reviewing just how people teach linear algebra, and there's three types of courses on linear algebra. The first is elementary linear algebra. This is what most universities give to all undergraduates, including but not limited to engineering, physics, and applied mathematics. And at UC Davis, this was Math 22A, if I remember correctly. And this begins by studying systems of equations, linear equations, and these pop up everywhere in applied math and economics and so on, which makes it frustrating to give a good motivation, because if you ask, well, why would I ever use this in life? And the answer is, well, you want an example? Everything is a system of linear equations. Then it's hard to pick out what's not a system of linear equations. We usually introduce an algorithm to solve these systems, Gaussian elimination. It's a little tedious. It's something like if you have n equations you're trying to solve, then it will take n cubed steps to solve it. So that's a little tedious, but you are guaranteed to solve it if there is a solution. This is usually when a segue is done to introduce matrix algebra. And the goal is to introduce something that's like numbers, but not number itself. And so we introduce new arithmetic operations for it, things like adding matrices or multiplying matrices. We need to check that it's well defined, that it obeys the operation identities that we would expect, like adding 0 to anything doesn't change the summand. And just as we would have factorization of an integer into primes, we'll have similar factorization schemes for matrices, so on and so forth. And this usually ends with the eigen decomposition, which is a particularly nice decomposition that lets us do calculations really quickly. And then at this point, there's a midterm, and everyone forgets what we learned. So we begin all over again by doing it as mathematicians would, by introducing a new gadget called a vector space. And whenever you introduce a new gadget, a pro tip is to introduce sub-gadgets, so subspaces, and ways to transform one gadget into another, a morphism, if you will. And that is precisely what a linear transformation does. And since this is a lower division course for people who are not mathematicians, usually this is done specifically in a coordinate system. So coordinates and bases are introduced explicitly, and change of coordinates. Let's see, once we have that, we usually talk about dot product, which measures how much a vector is along another vector. We'll get to it eventually, don't worry. But this gives us a notion of orthogonal vectors, unit vectors of length 1, and then the crowning achievement, the Graham-Schmidt process, which lets us take a collection of linearly independent vectors and produce a orthonormal basis. And then there's the final. And then it's over. So people are sad. For reference, the book we used was Introductory Linear Algebra by Coleman and Hill. So it was thoroughly mediocre, but it had a lot of exercises, which is good. Now, the second way to learn linear algebra is to learn it as math majors do, and I'm just going to call this the intermediate approach. UC Davis offered this as Math 67, if I remember correctly. And this jumps in really quite amazingly deep. Talks about fields of numbers, different number systems where you can do addition, subtraction, multiplication, division. Then talked about vector spaces over fields. So already we're starting with where we were after the midterm in 22A. So we then began talking about spans and direct sums and so on. Bases, dimensions. Usually we restrict attention to finite dimensional vector spaces because the results are just so much nicer. Linear transformations, kernels, images, and the invertibility of a linear transformation. Then midterm. And after the midterm, we started with eigenvalues and vectors. We talked about the determinant, as well as a more general dot product called the inner product, and a notion of length called norm of a vector. And this gives us, same as before, a notion of an orthonormal basis. Our good friend Graham Schmidt makes his comeback. His name is my name too. We have change of bases and how it affects linear transformations. And then we get into stuff that is not discussed in the lower division course, like self-adjoint operators, or even the adjoint operator. The spectral theorem, which talks about why the eigendecomposition is important. It turns out that eigenvalues of the matrix tell you everything you'd want to know about the matrix, and the eigenvectors fill in the rest of the details. And for sufficiently nice matrices, we can change coordinates so that it's purely diagonal. And if there's time, there's also different decompositions like polar and singular value decomposition. The singular values are a generalization of the eigensystem, eigenvectors and eigenvalues. Polar is a generalization of the geometric polar coordinates. And then there's the final. Again, people are sad. The third remaining way is, I guess I'll just call it advanced. At UC Davis, this was Math 250B, graduate course. At Caltech, it was Math 5B. So right after calculus, you're thrown into abstract algebra, and they're one of a kind. They end up making their students learn graduate level algebra as their second course. And here they're talking about modules over rings instead of vector spaces over fields. So a ring is a more general number system where you don't need division. Modules are just the analogous thing, like vector spaces. Then you talk about linear mappings between them, different decompositions, and it's really kind of a mess, but a beautiful mess. And it just depends on what number system you're working over. So I'm not going to get into advanced linear algebra too much. I'm just going to focus primarily on elementary. And if anyone's paying attention by the end, then maybe we'll go over intermediate. And if there's any interest, maybe we'll look at other things. Now, why would anyone be interested in linear algebra? It's not just a form of masochism, but from linear algebra, you can actually get a good peek into the, majority of the rest of mathematics. Because if you imagine it as a room, it's actually quite intimately connected to Fourier analysis, which is a way to solve differential equations or get insight into differential equations. And this is generalized in the field of functional analysis, which is linear algebra in infinitely many dimensions, which is a bit weird to get your head around. But you can do functional analysis basically in finitely many dimensions by doing numerical linear algebra. Numerical analysis is when you have the computer solve your hard math problem for you. Numerical linear algebra focuses particularly on linear algebra problems because it's so connected to everything else. Differential equations, which pop up in physics and really all of applied mathematics, because if you're interested in something changing over time, then you need to talk about its differential equation, or how it changes over space. Like the ocean's salinity changes smoothly with respect to temperature and location. So that would be described with differential equations. More interesting, perhaps, is differential geometry, which studies how do you do calculus on surfaces and in more abstract settings. Functional analysis is looking at calculus as if it were a linear algebra problem. Then we would have group theory, which studies symmetries, because an invertible matrix describes a symmetry of a vector space, right? And we can talk about how certain symmetries act on other spaces. Representation theory specifically looks at that problem. And we can talk about how a symmetry group will act on a surface or a geometry. Representation theory is responsible for that. Or the symmetries of differential equations. Again, that's representation. Well, people will disagree because everyone likes their own field and wants to be proud of it. And I don't want to besmirch any field. But it is, in my mind, a sort of representation theory to talk about the representation of a group acting on a differential equation. And I'm running out of space, but I could just keep going on and on. We basically have analysis, a good chunk of geometry, and a respectable representative of abstract algebra. So it touches upon everything you would ever be interested in. So if you want to look into these fields, linear algebra is a need to know. On the other hand, if you just want to peek your head into the workshop of mathematics and you want to see how mathematics actually works, linear algebra is the stepping stone into that. So it's a lot of fun. Don't forget to, let me see, I forgot the order of things. I think you're supposed to smash that like button and subscribe. Or maybe you're supposed to smash that subscribe button and like. I don't remember. So leave a comment below and let me know whether you're supposed to smash which button and click what. But don't forget to subscribe and like, and there'll be more videos coming out soon. So, yes.